Muy bien, gracias. Actually, I think this is the very first time that we are going to discuss Heron, never mind Pulsar, architecture here at Big Data Spain. So could you please welcome Ivan Kelly, who is software engineer at Streamlio, who came from Barcelona. Thank you very much, Ivan.
Okay. Thank you. So, hi, I'm Ivan Kelly from Streamlio, and today I'm going to be talking about end-to-end effectively once. At Streamlio, we're building a unified stream processing platform based around Twitter, Heron, and Apache Pulsar. So I'll be using these two systems to give examples throughout the talk. So what is effectively once? It's easiest to explain effectively once in the context of the other common stream processing semantics, which are at most once, at least once, and of course effectively once. Effectively once is also sometimes called exactly once, but we've been steering away from that term because it has proved to be a bit controversial. So what these mean, or what they're describing, is how many times a message will be processed in a stream processing system, which only makes sense in failure cases. So in non-failure cases, all executions in a stream processing system are exactly once, or effectively once. But in the case of failures, you may either lose messages or have to replay them, so this is where effectively once comes in. So to illustrate the differences between these semantics, I'm going to be using just this simple word count application, which we've already seen once today. You have a data source. It can be something like Twitter Firehose. Data is pushed from that data source into a messaging system, which carries the data to a stream processing system. And then in the stream processing system, you have a directed acyclic graph, which the data goes into the head of the graph. In this case, it's a splitter task, which splits the sentences into its constituent words. Then each word is sent to a different counting node, depending on the hash of the word. And then finally, the result of the word counts are dumped into some database for serving somewhere. Now, in this example, the count nodes are stateful, because obviously they need to keep a record of how many times particular words have occurred in a corpus, so state needs to persist there. So at most once is the simplest stream processing semantic. When data comes into the split node, it will split out the words, and then it will just fire and forget them to the other nodes in the graph. In this case, if there is a failure in one of the count nodes, state of that count node can just be thrown away, and the messages, the words which should be sent to that count node will just be dropped by the split node when it tries to send them. This can lose a lot of data, but with the at most once semantic, you don't really care. It would even be a valid at most once execution if you dropped every message that came into the system. At least once is a bit more complex. So with at least once, the sender, in this case the split node, and the receiver, in this case one of the count nodes, have a kind of agreement protocol between them, that the split node will not forget about a message it has sent until the count node has acknowledged it. So the count node will periodically dump its state into persistent storage somewhere, and when it knows that the state has hit persistent storage, all the messages which contributed to that state can be acknowledged to the split node, and the split node can forget about them. If the split node never gets an acknowledgement for some words, it will try and resend them after a while. Of course, there's no guarantee that the acknowledgement will actually get back to the split node, because we don't acknowledge our acknowledgements. You could keep going forever there. So it is possible that the split node will retransmit words which have already been counted, and this is why it's at least once. At least once you may count a word 100 times. Effectively once, and what has often been called exactly once, is slightly different and a lot more complicated. So what it doesn't mean is, it doesn't mean that a word a tuple or a word in our example will only ever be processed by a single node in your graph once, because it could be processed by that node, and then that node could crash immediately and the result would never get anywhere. So then you wouldn't have exactly once. What it means is that the result of processing that word in your graph will only be perceived in the overall result once. So if you have a corpus of 1 trillion words and the word faux only exists once, no matter what combinations of failures and crashes and whatever you see in your system, in the resulting count database, faux will only ever have 1 as its count. Well, it may have 0 if before it actually gets to counting that word, but at the end of your processing, you will only have faux counted once. And effectively once can be implemented in 2 ways, pessimistic and optimistic. And the difference between them, and the reason you choose one over the other, it's trade-off between how much I/O you want to use and how much of a latency hit you're willing to take in the case of a failure of one of your nodes. So I'll start with optimistic effectively once. And this is what's implemented in Twitter Heron. It uses an algorithm called Shandy-Lamport distributed snapshots. And what this does is, periodically, the system, this is tunable, periodically the system will insert a token at the head of your DAG, a directed acyclic graph. This token, when it hits a node, the node will immediately dump a snapshot of its current state to persistent storage somewhere. And at the same time, it will send the token out along all out edges of the graph to the next hop nodes. When the next nodes get the token, they also dump a snapshot to persistent storage. And once all nodes in your graph have dumped the snapshot for that token can be considered complete and it can be recovered from. In the case of a failure, let's say one of the count node fails or the split node fails, the whole graph needs to go back to the state of that snapshot, which means that all messages processed after that token will need to be processed again, and obviously you get a latency hit here. However, this is very cheap to run on your stream processing engine when the engine is in a stable state. So you can tune how often the token is inserted, and the snapshots can be taken asynchronously in the background. So the I/O load is pretty low, and you can tune it for how low you want it to be. Pessimistic effectively once takes a different approach. So in pessimistic effectively once, each time a tuple or a message is processed by a node, the node will generate a state delta, which is the difference between the difference in state before the node processed the tuple and after the node processed the tuple. And it will dump this to persistent storage and send the messages along. Now obviously this has a very high I/O load, because for each message you process through the whole graph, you are creating, in this case, for each message, you'll be creating up to 5 pieces of persistent storage. And this can get very, very heavy when you're running a very big graph. However, when you need to recover from this, you will take a latency hit only on this node that crashed, which is better than optimistic effectively once. Another thing to note, though, is that since you are persisting state for each message going through the system, you are taking a latency hit also on each message in the stable state, and this may or may not be what your application wants. So these are the systems that support the different kinds of effectively once. So Twitter Heron, which is part of the Streamlio platform, it currently supports optimistic, and we are developing pessimistic right now. So hopefully we'll have that soon. But so far I've only talked about the stream processing engine. And in our example application, there are many other ways to fail. So, of course, your stream processing engine can fail in many points. Your messaging system can fail. So you need some guarantees around your messaging system to ensure that you can provide effectively once. Whatever is feeding the data into your messaging system can also fail. So this needs to provide some guarantees so that we don't lose messages coming from there, and we don't duplicate messages coming from there. And finally, the database where you dump your final results into can fail. However, this is really just a materialization of the data that is already in the count nodes, and if you have effectively once in your stream processing system, you can reconstruct this pretty easily, so I'm not going to discuss the database anymore. So what do you need in your messaging system to provide effectively once? You need to guarantee that in the case of a failure, you don't lose messages. You need to guarantee that in the case of failure, you don't duplicate messages. And you should probably guarantee that you don't reorder messages. So Flavio Junqueira has a really good blog post about this, about how consensus is not necessary for exactly once. And the crux of his argument is that exactly once, the only guarantees that you're talking about with exactly once are no lost messages and no duplicated messages. However, in practice, if you have a stream processing engine and you don't have a guaranteed order on your messages, that means the stream processing engine needs to keep track of every single message it has ever processed so that it can track whether messages have been duplicated or not. And this just creates a huge amount of state in your stream processing engine. So this may be running for like days, weeks, months, years, and that just grows bigger and bigger as time goes on. If you contrast that to a messaging system which does provide a strong ordering, you can just keep a mark of what the last message you processed was, and everything before that message, don't process it again. Everything after that message, process it again. And that's only one single integer usually that you need to keep track of and forever. So while ordering is not necessary, it's very, very useful. And also, feeding on from this ordering requirement, you need to be able to reattach where you left off. And reattaching means, like, if you had to keep track of every message, how would you reattach to a messaging stream? You know, you'd have to send the messaging stream every message you ever had so that you could get what you haven't had before. It's not practical. And the messaging system needs to have ordering, but it also needs to provide you with an API that you can attach to an arbitrary point anywhere in the past. And finally, we have a non-functional requirement that catching up should not affect any other applications using your messaging system. If catching up affects other operations, it means that usually an organization will have 8 or 9, 10 data flows. They need catching up. If it affects the other data flows, you could end up having a cascading failure, and this could bring down your whole organization. You don't want that. So it's a performance requirement, but it's quite an important one too. And finally, once data gets into your messaging system, it's safe, but it still has to get there in the first place. So usually the messaging system needs to provide some guarantees on the publication side that messages will not, or data will not be lost, and that data will not be duplicated. So how do we implement this in a messaging system? So I'm going to be using Apache Pulsar, which is part of the Streamlio platform, to demonstrate. Just to give a quick introduction. It's been in production in Yahoo for 2 years, but really they've been building this for about 7 years. It's like an evolution of a number of systems. It's a distributed stream processing system, provides pub/sub and queue semantics, has some really nice, useful features like multi-tenancy and cross-data center replication built in from scratch. And it's open source for the last year, I think. It's a Apache incubating project. So how does Apache Pulsar provide the guarantees on messaging necessary for effectively once? So the guarantees we were looking for: no loss, no dupes, and no reorder. Together, these describe a property known as total order atomic broadcast. And total order atomic broadcast is known to be equivalent to consensus, or at least require consensus. So logically, the messaging system needs to either implement consensus, or it needs to use something which does implement consensus. Now, there are a number of systems available in open source which implement consensus. So there's Apache Zookeeper, even though you might be able to tell it from the logo, etc.d, and Console. But these aren't really suitable for building a messaging system on using them alone. They provide key value store type APIs, which isn't ideal for storing a stream of messages. You need something that looks more like a log. And also, though these do have a log, they're replicated logs with APIs on top, but these logs there's only a single log per cluster, which doesn't scale out. So for example, if you had a Zookeeper cluster and you wanted to increase the write capacity, there's nothing you can do really except throwing faster hardware at the nodes you have. If you add another node, you're just increasing the number of messages needed to add a single entry to that log, which it's a known problem, but usually it can be worked around. So how we work around it in Apache Pulsar is we use another project called Apache Bookkeeper. So Apache Bookkeeper is a horizontally scalable replicated logging system. It came out with the same group in Yahoo as Zookeeper came from. And what Bookkeeper provides is a building block called a ledger, which you can think of as a log segment. And on these log segments, which are replicated to a number of storage nodes called bookies, Bookkeeper provides guarantees that no messages will be lost, no messages will be duplicated, and no messages will be reordered. So total order atomic broadcast. It doesn't implement consensus itself. So it uses Zookeeper, in fact, a single write to Zookeeper per ledger or log segment to provide that the guarantee of no loss. So Pulsar takes these Bookkeeper ledgers, it builds a sequence of them and stores this sequence in Zookeeper, and this creates the replicated log for a Pulsar topic. So Bookkeeper also has some other very nice features which are super useful if you have a messaging system. So the storage nodes in Bookkeeper can take many, many streams of data which are being written to concurrently. Now, if you took a naive implementation of this, where you had each stream going to its own separate file on the file system, you'd end up doing a lot of random writes. And on rotational disks, this is death. On SSDs, it's still an orders of magnitude slower than doing a sequential write. So what Bookkeeper does is it has a interleaved storage format fairly similar to an LSM, but without a lot of the write amplification problems just because of the nature of the data that's coming in. And this allows us to store many, many streams concurrently on the same storage nodes. It also, related to this, it also isolates the read and the write path. So the critical path for writes goes to a completely different disk than the critical path for reads. And this is very important for our isolation requirement on catch-up. So if we don't want recovery to affect other applications in our system, we need this isolation, and Bookkeeper provides it. Pulsar, so going on from Bookkeeper provides the total order atomic broadcast. So the logs are ordered so we can reattach them. And Pulsar provides this with its API. The reattachment in Pulsar is done using cursors, which are kind of like offsets, but a little bit better. So usually an offset, you take a point in the message stream. Everything before this I have processed. Everything after this, give it to me again if I crash. With Pulsar, we have selective acknowledgement. So you can acknowledge message 1 and message 3, and not acknowledge message 2. So then when you reattach, you'll get message 2 again. And this can be useful in some use cases. And cursors are managed by Pulsar itself. So some systems, some messaging systems, they require that you manage the offsets yourself. The client either has to store them, or you need to spin up another system. Oh, nearly out of time. You need to spin up another system to store them. Pulsar doesn't do any of this. It takes care of it for you, and it stores them in Bookkeeper ledgers, which means that as you scale out your Bookkeeper storage, and Bookkeeper storage scales out very nicely because ledgers are just small little pieces that are just scattered among all the storage nodes. As you scale out your storage in Bookkeeper, your cursors also scale out. And this is important because for each topic you may have tens or hundreds of subscribers, and these will each have a cursor. So the metadata around keeping track of where each subscriber is can almost rival the primary data in your topics. And finally, for the publication part, the Pulsar provides idempotent publish. So usually when you're publishing data into your messaging system, it's coming from a flat file on your file system, or like an SQL table with an auto-incrementing field. You have some kind of number that's monotonically increasing, and Pulsar allows you to send this. So in the case of the file, it's the offset within the file. In the case of the database, or the database table, it's the auto-incremented field in the table. Pulsar allows you to send this offset with the messages as it's published. And the publisher will keep track of the offset for each publisher. And then if there's any failure in either the node publishing or the broker keeping track of the messages, because the publisher, if it sees the broker has failed, it'll have to retry everything it didn't get acknowledged on. It will deduplicate anything the publisher has successfully managed to publish before. And again, we store these publisher offsets in cursors. I'm running out of time, so I'm not going to go too much into why we do this. But so how do we bring this all together in the Streamio platform? So we have Twitter Heron, which provides both optimistic effectively once and pessimistic effectively once is coming soon. Our messaging system is Apache Pulsar. It provides cursors, so the stream processing system can reattach at any point in the past. It provides idempotent publish, so data coming from the data source is never lost or duplicated. And all this is built on top of Apache Bookkeeper, which provides a total order atomic broadcast primitive, and it scales to many managed storage streams, so it will scale as your application scales. So that's the end of my talk. If you have any questions, you can ask me now, or also we're on Twitter, so just send us a tweet. We also have a blog and a YouTube channel which contains a lot of technical info, going a lot more deep into it than I went today. So yeah, any questions? I can't see anything.
Okay, so any question? Right.
Is there anyone there?
Yeah. Okay. Well, that's very good.
Okay.
Anyway, thank you very much,
Thank you.
Ivan. Was right.